Hi, this is Computational Cardiology, and today we're going to be going over a lot of electrophysiology very quickly. Alright, let's start with the concept of an ion channel. So these are based on two ideas, permeation and gating. Permeation is essentially how ions get through open channels. Without permeation, all Nernst potentials would equal zero because all the cells would have an equal ability to get into the cell. And then as a result, there would be no signaling if all Nernst potentials were zero. Selectivity is how picky channels are for certain kinds of ions, while conductance is how well ions can pass through those channels. We're going to be referring to it as G, and it's 1 over resistance. In terms of gating, that is how channels open and close. There are a few different mechanisms for gating. You have voltage-gated channels, which open or close in response to changes in membrane voltage. You have ligand-gated channels, which open or close when something binds to them. And then mechanically gated channels, which respond to changes in stretch or pressure, think baroreceptors. Finally, you have ungated channels, which are leaky. The importance of having channels comes from the fact that ions are hydrophilic, while the membrane inside is hydrophobic. So it helps for them to have a way of getting through. We can define voltage here as the difference in potential across the membrane, and this is going to come up a little bit later. If we assume no membrane voltage difference imposed upon the cell and we just look at diffusion, we're going to be thinking back to Fick's law from biological models and simulations last semester. If the concentration of ions is the same inside as it is outside, there's going to be no net movement of ions, therefore no flux. However, if the concentration inside is greater than the concentration outside, the ions are going to want to move out of the cell. And this, by convention, we're going to say that positive ions moving out generates a positive current. And then looking at the reverse situation, if you have more ions outside than inside, you're going to be generating a negative current. Keep in mind here that if the ion's charge is negative, then these will be reversed. So negative ions leaving the cell is going to generate a negative current, and negative ions entering the cell is going to generate a positive current. Now let's say we impose a voltage across the membrane. If the concentration of ions is the same inside as it is outside and the membrane is positive, the way I'm going to think about this is that the positive ions are going to get pushed out of that positive environment. So there's going to be a positive current because we're having positive ions moving out. However, if the membrane voltage is negative, we're going to have the positive ions being drawn in, so that's going to be a negative current, or negative ions getting drawn out. If the concentration of an ion is greater inside than outside, then the voltage is going to be negative. And this is because the outward movement of the ion is going to leave behind a negative charge inside the cell. If we look over here, this is the Nernst potential equation, and it might be a good one to keep in mind. It's based on the gas constant, absolute temperature, valence, and Faraday constant, and then the natural log of the concentration of ions outside over inside. And then RT over F might be given to you, but if not, assume 25.8 millivolts. So again, this accounts for both diffusional and electrical forces. A few Nernst potentials that are good to keep in mind are that of sodium, which is 52 or around 50, potassium, which is around negative 96, chloride, which is around negative 56, and calcium, which is around 134 millivolts. And then there is more potassium inside the cell at rest and more of everything else pretty much outside of the cell. Since the cardiac resting membrane potential is dominated by Vk, it's going to be around negative 90 millivolts. If you are given different ion concentrations inside and outside of the cell, as well as their permeabilities, and you're asked to find the membrane voltage, you're going to want to use the GHK equation shown over here. Keep in mind that the outer concentration is used for the ions except for chloride, and that's because it has a negative charge, so that one gets flipped. Again, this considers permeability and concentration gradients. If we look over here, most of this class is based on the circuit analogy of the cell membrane. Here, the capacitor is a liquid bilayer that stores charge by separating ions across that insulating barrier or the membrane. The conductance accounts for the facts that ion channels are like parallel circuit pathways attached to the capacitor, which you can see here. And then the battery implies that each ion species has a battery equal to its Nernst potential. If we look over here at the formula for capacitance, you can see that it's based on the charge across the membrane as well as the voltage. And then if you take some derivatives, you're going to get this equation over here that essentially comes out to the capacitance times the derivative of the voltage with respect to time is the negative charge of the ions. And then if you're assuming steady state, you can use these simplifications that basically say that the membrane voltage at rest, keep that in mind, only can be used at rest, is essentially a weighted average of the conductances of different ions and their Nernst potentials. There's some situations that can arise if you get funky gradients. If you have low serum potassium, transmembrane voltage is going to go up, so you're going to have spontaneous action potentials. This is what happens in skeletal muscle if you get a Charlie horse ache. And then if you have high blood potassium concentrations, your heart is actually going to stop because it's going to have a harder time depolarizing. And this is a picture that I took with permission from the circulating nurse in an operating room, where you can see that they had actually stopped a patient's heart, and then when they reperfused it with blood, you can see it started beating again. I thought that was pretty cool. Let's move on now to Hodgkin-Huxley formalism. This starts with an experiment called the voltage clamp experiment, where they essentially took a squid giant axon, put it in a petri dish, and started getting these currents. The way it works is you hook it up with a membrane potential amplifier, a feedback amplifier, signal generator, and an ampere meter. Step 1 of this experiment is to measure the membrane voltage. Then you compare the membrane voltage to the voltage that you want to clamp. So that's what you're trying to reach. You can then inject current when the membrane voltage and the clamped voltage do not correspond, and then measure the compensatory current II. Using the formulas that we just looked at above, especially that the current is equal to the conductance times the change in voltage, you can see essentially what the current of a single ion type in that axon is. And the way they isolate these ions is by adding a substance that is impermeable. So for example, if you're trying to measure sodium, you can add choline. So that this way, if we're just looking at sodium and potassium, for example, the current that's clamped is equal to the current of only the isolated ion. So you'd have to do 2 runs per ion, one with a clamped and then one with a control, and you can take the difference from there. You can see here that if, again, we're operating with the assumption that we're only doing potassium and sodium, the total current is equal to the sum of the potassium and the sodium currents. From experiments like these, Hodgkin and Huxley actually figured out that the potassium channel follows a 4th order equation. And they realized that each component of this equation, of this conductance, is independent. So you can see here that we have GK equals GK n to the 4th, that's just showing our 4th order. They basically said that there are 4 independent gates when an ion is trying to get through. And the conductance there is based on the ability of each of these individual 4 gates to be open. They did some very fancy, very high-level math, and were able to establish the following equations. I'm not going to go through the derivation right now just for the sake of time, but I will show you that the final equation essentially goes that the probability of any one of these 4 gates being open is equal to this probability of being open at an infinite time, which is the opening constant over alpha plus beta, so the rate at which it's opening over the rate at which it's opening plus the rate at which it's closing. So it's equal to that PE at infinity minus the probability that it's engaged or enabled at infinity minus at 0 times e to the negative t over tau, where tau equals 1 over alpha plus beta, and alpha and beta are both functions of voltage. For the sodium channel, it looked a little bit different. Here, instead of having 4 gates that opened, you had 3 gates that were opening and 1 that was actually inactivating it, that was closing it. You can see here that the voltage for the potassium channel is increasing and then staying open, it's plateauing, versus for the sodium channel, it rises and then it goes back down. So they have 2 components, an M, which is an activation and it happens quickly, and then an H, which is inactivation and that happens slowly. You can see here that the equations are pretty much the same for all, just replace the different constants that you're using from N, M, and H. Let's move on now to the core conductor model, and it's operating off of two assumptions, that the current is one-dimensional and longitudinal, and then that if the current is diverted in the transverse direction, it encounters the membrane. So again, longitudinal this way, transverse this way, just so you can visualize it. I went ahead and defined all the relevant terminology, starting with the cross-sectional fiber area, the resistivity of the intercellular space, the conductivity of the intercellular space, total extracellular resistance per unit length, transmembrane current density, and the transmembrane current per unit length. If you see the equations, again, I'm not going to drive these for you right now for the sake of time, but these are the ones that you need to know. That the intracellular current is equal to 1 over the intracellular resistance per unit length times the intracellular potential, and this is based on Ohm's law, I equals VR, that's how it was derived. Then IE, same thing, just replace I with E. Keep in mind here that Ri is equal to negative Re. And then that Di, that the change in the current by change in space is equal to negative Im. You're losing current there, but then you're gaining it on the extracellular side. And then if you take the second derivative of both, you're going to get the Im equals Ri plus Re coming over. If we're looking at propagating waves, here's the wave equation. And then down here, as covered in lecture in this equation, keep in mind that the space constant, which describes how far you can go until the voltage has decreased by 1 over E, is equal to the square root of Rm over Ri plus Re, and tau is equal to Rm times Cm. Keep in mind that's a lowercase r because the other one is this multiplied by the circumference. If we assume a steady state, we're going to make 3 assumptions here. That we have an infinite length, that the current is injected at x0, and that dV by dt equals 0, so the capacitor in this case is fully charged. Here's the equation. You could replace this with Ri, and then just have it not be negative. And then you can take the derivative, and if you're trying to solve for the space constant, you would do it by starting off with a ratio of voltages at 2 different points, as you've seen in your homework. This equation also came from the homework, and this is what I was doing earlier to describe the difference between capital and lowercase r in this case. Moving on to action potentials, this is what a cardiac action potential looks like. It has 5 different phases. This is our resting potential, and it's dominated by Gk, so by the conductance of potassium. And then at 1, we have this upstroke, this really fast influx of sodium, and here Gna dominates. Then in phase 2, there's kind of a plateau situation, and here both Gk and Gcalcium dominate. And then phase 3 is repolarization when the membrane voltage drops again from its peak of around 0 to its resting potential of around -90. And here again we have our potassium dominating, as you can see by the graphs down here. I thought it was really interesting that during the upstroke, the membrane voltage doesn't reach the full 50 millivolt Nernst potential of sodium, and that's because it's open for such a short period of time before that inactivation gate closes. In terms of the different potassium currents that you might need to know, we're starting with the inward rectifier potassium channel, and this is responsible for keeping that membrane baseline potential. Then for the transient outward channel, this one's voltage activated again, and it initiates the repolarization that we saw. Then for delayed rectifier potassium channel, this one is responsible for that repolarization that we saw, and it's classified into 3 forms: slow, rapid, and these are both in the ventricle, and then ultra rapid, which is mostly in the atrium. Finally, you have that acetylcholine-based potassium current, and this one's ligand activated instead of voltage activated, and it lowers the baseline to a more negative potential. I also want to show you refractory periods. There are 3 that I find interesting, 2 that you need to know for the exam. You have absolute refractory period, during which no impulses can be generated or propagated. And for the sake of this class, it goes from the upstroke to around phase 3 of that action potential. For the sake of the class, assume this was within the absolute refractory period, but in reality, the absolute refractory period is within the effective refractory period. In this case, no action potential can propagate, even though one can be generated, which I thought was pretty cool. And then after that, from around the second half of the phase 3 to the end when you're repolarized again, you have your relative refractory period, in which case a stronger than normal stimulus would be needed to create an action potential. Pacemaker cells are a little bit different than those myocardial cells that we were just looking at. They only have 3 phases, 4, 0, and 3. During 4, the big difference here is that there is a creep upward.